All right, welcome back to our final video for Chapter 3 on chemical kinetics. In our previous videos, we introduced collision theory, we looked at how to measure reaction rates, we looked at this idea of rate laws, as well as a more mathematical approach to collision theory. Now we are going to discuss reaction mechanisms. Can we try to figure out a way to predict our rate laws based on the reaction that we have? And then lastly, we can take a moment to think about catalysis in the lens of biochemistry. All right, so reaction mechanisms are going to be our strategy for trying to predict a rate law for a given reaction. As we saw in our previous video, the rate law is a way to describe how our reaction rate is affected by our concentrations. And we said that this has to be determined experimentally. However, we have a way that we can predict the rate law based on some theoretical ideas. Our plan here is going to be looking at reaction mechanisms. Can we imagine a way where we can go step by step and picture the actual physical collisions that have to occur in order for our reaction to occur? These are what we call mechanisms. These mechanisms might be one step, they might be 2 or 3 or 4 steps. Right? We can have multi-step mechanisms. However, in our reaction mechanism, each individual step that we display has to be what is known as an elementary step. This elementary step occurs exactly as it's written, which means this is the exact collision that needs to occur. If these are the exact collisions that need to occur, well, we can determine the rate law for those steps in our mechanism because the collisions that are occurring need to follow this pattern. Whenever we have a single reactant turning into our products, well, this is just one molecule existing. This is going to be what we call a unimolecular reaction. This is going to be a first order reaction. Anytime we have two molecules colliding together, this is going to be a bimolecular reaction, and it is going to be overall second order. If we need two A molecules in the same place at the same time, we're going to have a second order reaction for A. If we need to have an A molecule and a B molecule in the same place at the same time, colliding together, we're going to have a second order reaction, first order for A, first order for B, overall second order. Notably, trying to have 3 molecules collide together all at the same time at the same place is going to be hard to do. That's going to be rare. And in fact, all of our mechanisms will be at a maximum bimolecular for each of our individual steps. All right, so our mechanism is composed of elementary steps where we can know the rate law for those elementary steps. Our mechanism has a series of steps that must add together to form our overall reaction. Right? If you add up all the steps in your mechanism, you should be left with the overall reaction that you care about. You might have chemicals that are formed from our mechanism early on and then consumed later on. These are known as intermediates. Alternatively, chemicals that are consumed early but then reformed later, these are known as catalysts. They also don't show up in the overall balanced reaction. We have a quick example here. NO2 plus NO2 forms NO3 and NO. This is our first step in our reaction. Right, 2 of these NO2s collide to make some products. In our second step of the reaction, we have NO3 combined with carbon monoxide to produce NO2 and CO2. For the overall reaction, we can combine together all of our reactants and all of our products. What we get on the reactant side is a lot of NO2s one of these NO3s and a CO. On the product side, what is left over? Notably here, we have some chemicals that are able to cancel out. This NO2 that we start with, but then we form again, maybe one of these NO2s could be considered a catalyst. NO3 that we form early on in this mechanism, but then use up in our subsequent steps, would be considered an intermediate. Overall, what we get is something like this. And there we go. Our mechanism is a couple of elementary steps where we're displaying exactly what has to collide. Our overall reaction is, well, just some chemicals combining together to form some products, not necessarily representing the physical collisions that need to happen. We have another practice problem. Let's pause, see if we can get it. All right, for each of these reactions, we want to write the rate law. Our rate law is going to have this form. For our elementary steps, we actually don't even have to do experiments to figure out the exponents in our rate law. For elementary steps, we can say that the rate is equal to K times our reactants raised to whatever their coefficients are. Since we have two chemicals colliding, we call this a bimolecular reaction. Likewise, for this second reaction, well, normally we would have to do some experiments to determine those exponents in our rate law. But since this is elementary, we have those molecules physically colliding. Our rate has to be equal to our rate constant times those chemicals, well, raised to whatever coefficient is next to them. First order for carbon monoxide, first order for chlorine, once again, an overall order of bimolecular, overall second order. All right, our goal was to determine our rate law for our overall reaction based on these mechanisms. And the way that we have to do this is by thinking about our rate limiting step. If you have a series of things that need to occur, well, we're limited by the slowest thing that can happen. Right? We have a bottleneck. We have a rate limiting step. If you're trying to drive across the country and it's going to take you, 15 days to drive across country, does it matter how fast you go from your door to the end of the driveway? Well, probably not. The bulk of that trip is based on whatever the slowest part is. The big trip across the entire country, not the fast step of getting to the car in the first place. Likewise with our mechanisms. Oftentimes we are going to have some steps that are orders of magnitude slower than our other steps. That slowest step will dictate how long this reaction takes. Here we have that example from the previous slide. If we have these two steps of our mechanism, well, part of the mechanism is to display which step is the slow step. Right? That step is going to be the bottleneck in our reaction, is going to dictate how fast the reaction can go in general. What we can say is our overall rate of the reaction is equal to the slowest step in our reaction. And conveniently, since that is an elementary step, we know the rate law for that step. The rate law for this step 1 is equal to our rate constant times our concentration, well, in this case, squared. A thing to note, we said our overall reaction was this. If that's the overall reaction, then our rate law has to be in the form that we would expect for that overall reaction. In other words, the rate law has to look like K times NO2 to some exponent times CO to some exponent. If we just had the overall reaction, we would not know what those exponents are. Since we're proposing this mechanism, well, we can figure out what those exponents should be. We should have an exponent for nitrogen dioxide. Well, based on the mechanism, it's 2. We should have an exponent for carbon monoxide. Based on our mechanism, it is Well, 0 means that it doesn't show up. And this rate constant is going to be the same as, we call this K1, the rate constant for step 1 in our mechanism. And there we go. That's our plan. We can list out our elementary steps. We can indicate which one is the slowest step. And that slowest step will dictate the rate law for our overall reaction. Well, sometimes there's a problem. Sometimes our slowest step is not in the correct form. Maybe it has an intermediate. Our rate law can only be our reactants and maybe our products, but it can only be chemicals that show up in our overall reaction. If you have an intermediate, this does not show up in the overall reaction, and we have a problem. To rectify this, we can use the fast equilibrium method, which says if we have a slow step, everything before that slow step can be considered at equilibrium, where the rate of our forward reaction and the rate of our reverse reaction are the same. Both forward and reverse reactions happening at the same exact rate. Mathematically, here's our equation. Well, also mathematically, we can write the rate law for our forward reaction. We can write the rate law for our reverse reaction. And we can try to rearrange this equation so that we can have an equation for our intermediate only in terms of chemicals that we care about. We can fix our rate law for the slow step so that it is, well, the form that we want it to be. All right, here's the problem. We have our overall reaction. For this overall reaction, we want to figure out the rate law based on a certain mechanism. Well, since we know the overall reaction, we know what our rate law looks like. Some rate constant times our reactants raised to some exponents. For some random overall reaction, we don't know what the exponents are. In fact, normally we have to do a lot of experiments to figure out those exponents. With our mechanism, we can also try to predict them. So, okay, this mechanism says that our slow step is the second step, and so the rate of our reaction is based purely on that slow step. The rate for step 2 is some rate constant times NOBr2 times NO. Well, we want this equation to look like this up here, but there's a problem. NOBr2 does not appear in our rate law expression for the overall reaction. Our next plan, we need to use our fast equilibrium method. Since our slow step is later on, everything above it is able to reach that equilibrium. So the rate of step 1 is equal to the rate of step 1 going backwards. This -1 notation means going backwards. We can write out our rate law for step 1. We have NO and Br2 colliding. Our rate law is K times NO times Br2. Because we have elementary steps, we can certainly predict that rate law. For step 1 going backwards, we have some rate constant. We can use that -1 notation to mean reverse. And then our only product here, the only chemical in our step 1 going backwards, is NOBr2. So we have a first order reaction for NOBr2. Because this is equilibrium, step 1 going forwards is the same rate as step 1 going backwards. And so we can tie these two pieces of our equation together and end up with, well, an expression for NOBr2. And that's what we want. We wanted to replace this in our equation up here. So let's solve for it down here. Once we have this expression for NOBr2, that intermediate, we can substitute all this over here into our rate law from our slowest step. What we get is this expression. The rate for the slow step is a bunch of rate constants multiplied and divided by each other times NO times Br2 times NO. If we want to combine terms, we can definitely do that. And our result is that our rate is equal to a bunch of Ks times NO to the second power and bromine to the first power. Our goal was to figure out this rate law. Now we know that our order for nitrogen monoxide is 2. We know that our order for bromine is just 1. And, well, additionally, we have our rate constant for the overall reaction is based on the rate constant for our steps in our mechanism. We have one last practice problem here. We can test this out, see if we can get it. All right, what we find is that, well, we want our rate to be dictated by the slowest step. So this is just going to be step 1. The rate law for step 1 is going to be HBr times O2, both of these to the first power. And is this okay? Can we have HBr in our overall rate law? Yes, we can. Can we have oxygen? Yes, we can. Do we have anything that we don't want in there? No, this looks good. Seems like we have a nice rate law for this mechanism. All right, so there we go. We can look at our mechanism, and based on what our slow step is, we can predict the rate law for our overall reaction. Notably here, our rate laws are, well, theoretical. These mechanisms are things that we are proposing. They might be true, they might not be true. We actually need to test our mechanisms to prove that they are valid, or to disprove them and find a better mechanism. So, okay, if you want a good mechanism, it needs to add up to the overall reaction that we have. It needs to include our slow step, which will dictate the rate of the reaction. Our mechanisms can be unimolecular steps or bimolecular steps. And any experiments that we do should agree with the mechanism that we're proposing. Notably here, scientific method, we are not proving that our mechanisms are true if we do an experiment, but we at least have some data to support it. If you ever have an experiment that disproves your mechanism, you can throw it out and try to come up with a new mechanism. Right? And you can come up with an infinite number of mechanisms for any given overall reaction, and not all of them certainly can be what actually happens physically. We can switch gears for just a moment here and think about catalysis. We have mentioned catalysis previously. This is a way that we can increase the rate of our reaction. Right? This is important. We want to be productive. We want to reduce costs. We want to have, maybe very specific reactions occurring. We can catalyze reactions to make sure that they are the ones that are happening, to make sure that it's happening as much as possible, to make sure it's happening as efficiently as possible. In biology, this happens a lot, actually. A lot of biological reactions are catalyzed by enzymes, by biomolecules that are functionally designed to do a very specific reaction. Notably, when we have a catalyzed reaction, what we're doing is we're introducing an alternate mechanism. On our reaction coordinate, we're trying to go from the reactants to the products. Well, we can take an alternate path when there's a catalyst present. If there's not a catalyst present, maybe we have to take the long way there. And on these types of graphs, the height of the graph indicates the activation energy, which is related to how fast the reaction can go. This shorter activation energy means that the reaction can go much faster. Here's an example for us. We have some mechanism, ozone combining with oxygen to produce, oxygen molecules. This is a slow reaction that occurs in the ozone layer of the atmosphere. Right? High up in the atmosphere, there's some ozone, this O3, which in small amounts is nice. It helps protect us from UV radiation from the sun. Well, if this is a slow reaction without a catalyst, chlorine as a single atom is able to catalyze the reaction. We can form this ClO molecule as an intermediate, which then is able to very quickly react with oxygen to form oxygen molecules, and once again, that Cl atom. Chlorine is there in the beginning, chlorine is there at the end. Even just a single chlorine atom can react with many, many, many ozone molecules, causing them to decompose. Right? So this catalyst allows this large hole in the ozone layer to start to form. The work done studying this reaction and this mechanism was awarded the 1995 Nobel Prize in Chemistry to Paul Crutzen, Mario Molina, Sherwood Rowland, and it led to some environmental policy changes. The 1987 Montreal Protocol limits the amount of chlorine-containing molecules that can be used in things like refrigerants. As a result, you don't hear too much about the hole in the ozone layer anymore because we're doing a better job about not letting these chlorine atoms out into the atmosphere, because even a small amount of them, they can interact with many, many, many ozone molecules. If we want to do some calculations with our catalysts, well, we can use that Arrhenius equation, right? The activation energy is going to be different for our different pathways. Maybe we're able to measure that. We're asked to calculate here how much faster will our reaction go when we have this difference in activation energies. Our strategy can be, can we find this ratio of catalyzed versus uncatalyzed rate constants? And so there we go. Let's set it up like this, where we can, abbreviate cat for catalyzed and un for uncatalyzed. We start to see a few things drop out and our calculation becomes a little bit easier. Maybe we have the same value for this frequency factor. And the rest of these values we can plug in. We know the value for the temperature. We know the value for our activation energies. We know the gas constant in units of joules per mole Kelvin. Ooh, that is a good note. Let's be careful here. If we're looking at our gas constant in joules per mole Kelvin, let's make sure it matches up with our units for our activation energies so that we can get a good answer where all of our units line up. Let's quickly run through some different types of catalysts. We can have what are known as homogeneous catalysts. These have the same phase as the chemicals they're interacting with. So as an example, we could have our chlorine atoms interacting with ozone up in the atmosphere. There's our example once again, right? 1995 Nobel Prize. We can also have what are known as heterogeneous catalysts. These have different phases than the chemicals that they're interacting with. Oftentimes we can have gases interact with a metal surface, right? Metals are a nice source of electrons, a nice source for our molecules to adsorb and move around freely. In this reaction, we can catalyze our addition reaction onto our double bonds in these organic alkene molecules. We said before that these double bonds are extra reactive. Well, these molecules can all absorb onto our metal surface, make it easier for them to interact with each other. We can have our hydrogen molecule absorb onto the surface, our alkene molecule absorb onto the surface, and then they can move around, start to form some intermediates, and finally, our final product. For these heterogeneous catalysts, there's this typical process: adsorb onto the same surface, have our reaction occur, and then desorb, go off into the phase that we started with. In biology, we have a little bit different terminology, but we also have, lots of catalysis happening. Our biological catalysts are known as enzymes. These enzymes are oftentimes proteins, where, our proteins are a string of amino acids bonded together. That string of amino acids starts to fold up into some typical patterns of spirals and sheets, and then starts to fold up into a three-dimensional shape. Oftentimes we have a couple of these molecules bonded together or grouped together. We get this primary, secondary, tertiary, quaternary kind of structure building up from our amino acids into these big functional protein molecules. Our terminology here: The catalyst in our reaction is known as an enzyme. Our reactants can be known as substrates. That transition state that we form is an enzyme substrate complex, ES with this double dagger symbol. Our product is still the product, but the reaction rate might be called the velocity. Otherwise, same kinetics, just different terminologies. On our enzyme, there is an active site. This active site allows us to bind with the substrate, facilitates the reaction occurring, and then allows the product to pop away. This active site is going to be specific for a particular substrate. Right? This allows us to make one particular reaction much, much faster. The ways that we can have a specific substrate, maybe we have a lock and key kind of mechanism. Maybe we have a lock and two key kind of mechanism. Maybe we have some kind of floppy active site that binds to our substrate when it appears. A few different ways that we can think about these active sites. Regardless, they are going to be specific to our substrate, and they are going to allow our transition state and allow our products to form much easier and much more quickly than they would without that enzyme. All right, that's going to be our focus for this class. Thanks for hanging in there on chemical kinetics. Hopefully we have a better idea of, well, why different reactions go at different rates, how we can measure that, how we can relate that with our rate laws, and finally, okay, we can use our mechanisms to try to predict these rate laws to get a better intuition of what steps might be occurring as our reaction unfolds. Finally, catalysis, we have a little peek into biochemistry and some fun stuff there. Thanks for watching. Thanks for being here. Please let me know if you have any questions, and I hope to see you all in the next video. Until then, have a great day.